Hi, this is lecture one for week 5 of CS 1030, and this week we're going to sort of move on to a completely different topic from what we were talking about before. We're going to start talking about number systems, and in this first segment will be pretty easy, and things will get a little harder over the subsequent ones. But by the end of this week's lectures, we're going to be in some kind of genuinely difficult material. So I want you to pay attention if you can to this stuff, because this, like I say, there's going to be sort of a progression of getting harder, and by the end, it's going to be some stuff that actually probably will be challenging for you. So start off looking at number systems. So early in sort of modern human history, people counted using number systems that were really different from the ones we have now. And early number systems often came from sort of the idea that you would count things on your fingers. So we count things on our fingers. We can count one thing per finger. And so sort of the natural way to abstract that, to sort of use it in a, write it down or use it in a different context, is to use tally marks. And so tally marks are essentially these kind of systems like we're seeing on the right part of the slide here, where there's one mark corresponding to one thing. So if we want to count 5 things, we have to have 5 different marks. So this is fine. It works. There's no problem. We use this, of course, every day when we're just counting things on our fingers, just around the house or whatever. But it turns out that doing math operations with tally marks is sort of a problem. And to sort of start to see the problem, imagine writing the number 1 billion in regular decimal number system. That's not that hard. What if you had to write a billion with tally marks? Well, if you could write 1 mark per second, this would take you like 34 years. So you can't really write down a billion. You can't really do mathematical operations on large numbers. So the sort of tally mark system is something that that basically is good and fine for very small numbers, very sort of casual arithmetic, but it doesn't scale to kind of just to sort of more serious applications. So more modern than the tally mark system are systems such as Roman numbers. So Roman numerals are more sophisticated than a tally system in a sense that they can represent larger numbers than tallies can without becoming incredibly cumbersome. But so, as you know, if you've studied Roman numerals at all, they're really weird and awkward. So we have an idea here where, as you can see on the right part of the slide, we have sort of different marks standing for different things. So the vertical, the vertical slash means 1, and V means 5, and there's some other numbers mixed in. And then there's this very weird subtractive notation where we represent 4 by saying 1, 5. So the fact that the 1 is before the V, the I is before the V, means that the value is subtracted. Whereas if we had the I after the V, then it would be added and it would become 6. And so the position of the characters is not important in Roman numerals except for the subtractive versus additive element. Other than that, the position doesn't matter. So let's sort of think about like doing something like your taxes in Roman numerals. That's going to be hard, right? Doing math on this kind of mixed additive and subtractive number system is just not really particularly easy. This is almost certainly kind of imposed some sort of a tax on accounting in the Roman Empire. And I have no idea if this was actually a problem for them or not, but you could imagine that doing real engineering or real science or real accounting would not have been particularly easy in this kind of a system. So the point of talking about these different number systems here is not to do some sort of a history view, but rather we're trying to make the point that the choice of number representation is purely an engineering decision. What I mean by engineering decision is we can make any design we want for a number system. We can do it any way we want, and any system we choose is going to make some things harder and some things easier. So this is sort of the essence of engineering trade-offs, and it's not really that different than choosing something like a programming language. No matter what you choose, it's going to make some things easier and some things harder. So now let's talk about the engineering choices made to come up with the number representation that we use, sort of in day-to-day life. And the general term for this kind of notation that we use is positional notation. And the essence of positional notation is that the position in which each digit appears is extremely important. That determines its value. And this is so familiar that it's hard to sort of think about, but what we want to try to do is step back a little bit here and analyze the number system we're using, because once we start getting into computer number systems more, we'll see that there's quite a few sort of weird and interesting number systems that we've developed for use within computers. And the more we understand about sort of how number systems work in general, the easier it becomes to understand the trade-offs, the engineering trade-offs involved in computer number systems. Okay, so we're not talking about computer number systems yet. We're just talking about our number system, the one we always used, the decimal system. And we can ask, what does 382 mean? Well, I already said it, right? The 2 digit contributes 2 to the value of the total number. The 8 contributes not 8, but 8 times 10. And we know that because it's one place left of the ones place. It's in the tens place. So that's, of course, what we call it. This is what we all learned in third grade or something. The 3 lives in the hundreds place, so the 3 contributes 100 to the value, or 300 to the value of the number. And so the total number that we get is 382. So again, this sort of positional aspect where there's a multiplier, this sort of implicit multiplier based on where the number sits, is really important. And it turns out that this gives, this is sort of a good engineering trade-off. This gives some nice properties. We can represent very large numbers with a relatively small number of digits, so that's good. We can do math on these positional numbers using fairly simple algorithms. And you know the algorithms, of course, even though you haven't necessarily always thought of them as algorithms. We learned them all in grade school. And so this, like I say, so this sort of is a nice number system for many purposes. We haven't really necessarily come up with any improvements for human purposes, although again, when we look at computer number systems, we'll see that the computer number systems work quite a lot differently. Well, no, sorry, they're still positional, but they have different, there's different things about them. And then one thing that's really important in a positional number system is, since the position matters, you can't just sort of move something to the wrong place. And so we use zeros as placeholders when we're writing out long numbers to make the other digits appear in their proper places. So again, this is an invented representation for numbers. This is purely something that humans came up with. There's nothing, in the universe which says we have to use this kind of a number system. We sort of agree on the meaning, and then we can interpret numbers in this system. And the deeper point that I'd like to make here is that numbers, in kind of an abstract mathematical sense, don't have a notation. They don't have a base. They just exist. They're kind of out there floating in space. And so the number 5, mathematically speaking, what it means is 5 things. And we can express 5 things using any number of different number systems, and we've seen several of them in this lecture segment here. And but like I say, the thing that's easy to get confused is because we've spent so much time with the positional number system, with the decimal positional number system, it's kind of easy to start confusing the way we write numbers with what the numbers actually mean, and that's going to get you into trouble in this class. So we want to start making a distinction between these two different things. So one of the first ways that we're going to sort of start looking to generalize what's going on here is by looking at different bases. So the meaning of a number in a positional number system depends on the base. And the base just means what is the multiplier that you use to get from one position to the next. And so we obviously, of course, work in base 10, or the decimal number system. And what all that means is that as you move left in the number, a digit in the next place is always worth 10 times what a digit would have been worth in the previous place. So we have the ones place, the tens place, the hundreds place, and of course the thousands place. And that's really important. And so the positional number system is the first engineering choice I wanted to talk about here. And the decimal positional number system is sort of a variant of the positional number system. And it's, of course, the one we use. And again, this is just sort of something that humans invented, and it seems to work pretty well. And there's any number of other things we could have done, but they're not. This is what we do. So let's talk about one more thing before we finish this lecture segment, which is that we'd like to talk about exponential notation. So if we see 10 to the 2, so we always say to the whatever when we use the little superscript here. So 10 to the 2 means 10 times 10. So it means there's 2 10s multiplied together. So then clearly 10 to the 3 means 10 times 10 times 10, or 1,000. And then this all should be pretty intuitive, but something that's maybe a little less intuitive is that 10 to the 0 doesn't mean 0, it means 1. And that sort of keeps everything consistent, and it seems a little arbitrary, and we just have to keep it in mind. It's just how it works. So now this gives us sort of a little bit different way to look at positional numbers in the decimal system. The number 382 means 3 times 10 to the 2 plus 8 times 10 to the 1 plus 2 times 10 to the 0. And the same trend would keep going to the right. We would start going to negative exponents, and to the left, and we would be going to higher positive exponents. So the general pattern is that decimal numbers work in a way that the exponents sort of form a number line. They go from negative infinity to infinity, and sort of course, the numbers we usually work at are sort of not too far from 0. So just before we finish up this lecture, let's just review a little bit. So if you don't mind, pause the video for just a second and work out what each of these numbers is, and then unpause. Okay, so what is 10 to the 5th? 10 to the 5th is 10 times 10 times 10 times 10 times 10. And another way we can think about that sort of more easily is it's a 1 followed by 5 zeros. So what's a 1 followed by 5 zeros? Well, it's just 10,000. 10,000? No, 100,000. Shoot. 10 to the fifth is 100,000. Okay, 10 to the 9 is 10 times 10, 9 times. And so that's a 1 followed by 9 zeros, and that's going to have to be a billion. Okay, and we haven't really talked about negative exponents yet, but the way it works is the value of the multiplier keeps getting divided by 10 every time. And if you remember, 10 to the 0 is worth 1. So 10 to the minus 1 is worth a tenth, and 10 to the minus 2 is worth 100th in that case. So it's the way you can think of it is 1 divided by 10 times 10. So that's how sort of we can interpret the negative exponents. Okay, so this has been sort of an introduction to positional number systems, and we're going to continue with number systems in the rest of the lecture sections this week. Thank you.